Hey, welcome back to Graph Theory. In this lecture, we're going to continue our work on planar graphs, still in section 9.1, and this time we're going to state, not fully prove, but state a complete characterization of actually planar graphs due to Kuratowski. All right, so in this second lecture, you can see the goals there. What I want to do to you is give a proof that K5 isn't planar. I want to give you a proof that K33 isn't planar. And then look at this surprising characterization due to Kuratowski of non-planar graphs. If you don't like these proofs, they're a little hand wavy because, you know, some of the geometry of the plane here, we just don't have rigorous tools. So I'm going to be using this Jordan curve theorem again without license. But if you don't like these proofs, then in our last lecture in section 9.1, when we talk about bounds on the sizes of planar graphs, I can maybe give you a more satisfying proof that K5 and K33 aren't planar. But let's see what you think of these. So what did we do last time? We drew planar drawings of the complete graphs, K1, K2, K3, and K4. So K5, given that, is the smallest complete graph that's not planar. And let me try to convince you of that. So the theorem is that there is no planar drawing of the complete graph K5. All right. So how do we start? Well, K5 has a spanning subgraph that's isomorphic to C5. It's got a cycle of order 5 in it. And that subgraph makes a simple closed curve. And so according to the Jordan curve theorem, that simple closed curve has two regions. It's got an inside and an outside. Okay. So we have to add the remaining 5 edges. And at least 3 of them are going to end up on one side. Yeah, because as you start adding edges, well, you have to add an edge inside or outside. You have to add an edge inside or outside. And because 5 is an odd number, the number of inside edges and outside edges will have to end up splitting 3, 2. So or I shouldn't say that, but there has to be at least 3 edges on one side. And without loss of generality, I might as well assume it's the inside, because otherwise I can just write the whole proof switching inside and outside. Okay, so we have to have at least 3 edges inside. So I start adding these edges. So I've drawn one of them here, and notice that when I draw that new edge inside, then it isolates one of the vertices away from the remaining 2. Yeah, no matter where I drew it. If I drew that edge, say right here instead, it would isolate this vertex away from the other 2. So when you add that first inside edge, it separates the vertices. So that only allows us to draw one more edge inside with no crossing, because that vertex that gets separated, it can't be drawn, it can't be connected to any of the other vertices without inserting a crossing. All right, but we said we were going to have 3 edges inside, so that's our contradiction. So K5 is a non-planar graph. That's one proof of it. Here, I want to prove to you also that the complete bipartite graph K33 isn't planar. These seem like sort of specialized things to be picking, but you'll see with a big story here in a second. So K33. Okay, well, K33 has a spanning subgraph isomorphic to C6. Yeah, K33 is a complete bipartite graph. I've colored my partite sets here black and red, and I've labeled the vertices, the black ones with capital letters, the red ones with lowercase letters. And I've got this subgraph isomorphic to C6. It's an even cycle. It's a bipartite, 2-colorable cycle. So label the vertices as I've shown there. And then this is a complete bipartite graph. So the vertex capital A, which is in one of the parts, has to be adjacent to the vertex little a because it's in the other part. And that edge has to be either inside or outside by the Jordan curve theorem. So without loss of generality, let's draw it inside. Okay, so you can redraw this proof if you want putting this out, but I put that edge inside. Okay, but then as soon as you draw that edge, then you can see, if you don't want any crossings, both the edges BB and CC, which again have to be in this complete bipartite graph, you have to draw them both outside, because inside they would both give crossings. Yeah, we're trying to avoid crossings. But as soon as you pick one, say BB, no matter how you try to draw the edge outside the BB, you're going to isolate the vertex either little c. I just isolated little c. I can't connect it to capital C without a crossing now. Or if you went this way to connect BB, then you've isolated capital C. But either way, you can't draw both edges outside without a crossing. So K33 is not planar. Cool. All right, so those are kind of two negative results here. Here's something a little bit more positive. The complete bipartite graph K2n is planar for all n greater than or equal to 1. And here I've just drawn the planar graph. That's my proof. The bipartite sets are red and black. I've drawn the red one has two elements in it. The black one has the other end, and that's how you can draw a planar version of it. So that bipartite graph is planar. Excuse me. It's been a long day and I'm losing my throat here. I'll try to make this quick and stop coughing. So here's a little theorem that's not so bad to understand. If you take a subgraph of a graph G and it's not planar, then your graph can't be planar. That's kind of an obvious thing because any planar drawing of G would give rise to a planar drawing of any of its subgraphs. So if H can't be drawn planar, then you can't draw G planar, all right? So as a big corollary of that, we can kind of milk a lot. We proved above that K5 isn't planar. Well, K5 is a subgraph of Kn for any n greater than or equal to 5. So there are no more complete graphs that are planar. They're all non-planar as soon as n gets to be 5, and in some sense, it's because of K5. They contain a K5, so they can't be planar. So K1, 2, 3, and 4, planar, never find another planar complete graph again. If we apply this same theorem to what we proved about K33, we have this corollary, that K3n isn't planar for any n greater than or equal to 3. Because again, K3n contains K33 as a subgraph. K33 is not planar. Okay, then once you have that, once you know that K3n isn't planar for all n, you can step it up. You can say no complete bipartite graph where the parts are at least 3 is planar, because Kmn contains K3n for all m greater than or equal to 3, right? So you can kind of chain your way up on these things. Okay, we're working up to this characterization. We need one technical definition. Let me just show you the example while we're looking at it. So a subdivision of a graph, it's kind of a weird operation. I've taken this graph G. A subdivision just means that you insert vertices along edges in G, always making the new vertices have degree 2. All right, so you can pick here. I can even do this on the fly if you want. There's a subdivision H, you're looking at it. Now I made it a new one. Now I made it a new one. These things are not isomorphic. You can check that with degree sequences. Yeah, I'm changing the number of vertices of degree 2. These graphs don't have the same order. All right, so, and in fact, G is even a subdivision of itself. You don't have to put in any vertices at all. So that's this notion of subdivision. So in the 1930s, Kuratowski proved the following very surprising result, that a graph G is planar if and only if it contains no subgraph that is isomorphic to a subdivision of K5 or K33. So in some sense, I mean, allowing for subdivisions, the non-planarity of K5 and K33 is kind of responsible for the non-planarity of any non-planar graph. If you give me a non-planar graph, right? So just look at the contrapositive of this. If G is non-planar, then it must contain a subgraph that's isomorphic to a subdivision of one of those two things. So K5 and K33 are sort of the reason, again, allowing for subdivisions, that any graph is non-planar. The proof of this is, I wouldn't call it hard. It's technical and lengthy. It's definitely not in the spirit of the kind of stuff. And also, it needs a little bit of geometry that we're just not developing here about. I've kind of given a little pretty hand-wavy version of planarity, but to make this stuff rigorous, you kind of have to speak about embeddings of curves in the plane, and you have to be a little bit more careful about your geometry and topology, and we just don't have those tool sets here, so we're not going to worry about it. But I don't want you to think that the proof of Kuratowski's theorem is something that you couldn't possibly understand. You could all understand it. You just need to develop a little bit more machinery than what we're doing here in this course. Part of it's not that bad, though. We can prove sort of one part of this, because if G has a subgraph that's isomorphic to a subdivision of one of these things, subdivisions don't affect planarity. Yeah. If you have a planar drawing of a graph, you can subdivide it, and you're not going to make it unplanar. You're just putting vertices along edges of degree 2. So subdivision doesn't affect planarity. So if G has a subgraph that's a subdivision of K5 or K33, it couldn't possibly be planar. Yeah, because those graphs K5 and K33 themselves aren't planar. So if you had some planar drawing of G, then you'd have some planar drawing of this subdivision, and then you could kind of remove those vertices. You get a planar drawing out of K5 from that. Yeah, so by the contrapositive of that, if G is planar, then it can't have any such subgraph. So that's half of Kuratowski's theorem. It's not the lengthy half. Okay, so we're going to keep this video super short. It's just this characterization. The highlights of the lecture are that the complete graph K5 and K33 aren't planar. And in some sense, in this subdivision Kuratowski sense, they're the reasons that any graph isn't planar. Next time, Friday, what we'll do is take a look at one more topic in section 9.1 about number of edges in planar graphs. We'll get some bounds. They'll give us alternate proofs that K33 and K5 aren't planar. And then we'll move on next week, week 15, we'll look at some notions related to planarity and coloring, and try to get to a place where we understand the statement of a very famous theorem in graph theory called the four-color theorem. Okay, so thanks for listening.